In this video, we're going to be talking about how to find the product of two complex numbers and then write the product in polar form. So we're actually going to do this a little bit backwards. Given two complex numbers, and remember a complex number is a number which is the sum or difference of a real number and an imaginary number. So for example, this is a complex number, z equals 2 root 3 minus 2i, where I is the imaginary number. 2 root 3 is the real part, and this negative 2i is the imaginary part. So we have the difference of a real number and an imaginary number, so z is a complex number. So we have two complex numbers, z and w in this example, and what we want to do is multiply these together. We want to find the product, and we want to write that product in polar form. The easiest way to go about doing this is to write each of these complex numbers individually in polar form, and then to find the product of these numbers after we've written them in polar form. So the first thing we want to do is write these numbers in polar form, and we've done this in a previous example. Before we do anything, we want to look at the real part and the imaginary part of the complex number and quickly plot the number in the argand plane. And remember, in the argand plane, we have the real axis and we have the imaginary axis. So the real part is 2 square root 3. Well, that's a positive number. So we're going to go out in the positive direction along the real axis. So start at the origin and go out in the positive direction along the real axis. The imaginary number is negative. It's a negative 2. So we're going to go in the negative direction of the imaginary axis. So we're going to go positive along the real, negative along the imaginary, and we're going to end up, let's say, for example, at about here. The most important thing is identifying which quadrant this imaginary number is plotted into. So in this case, we have quadrant 4, and the reason that's important is because quadrant 4 then is the quadrant we'll be looking in to find the value of theta when we get to this formula here, tangent of theta equals beta over alpha. So we've got quadrant 4. What about this complex number? W is equal to negative 1 plus I. Well, the real part is negative 1. The imaginary part is the positive 1 coefficient in front of this I value that isn't written, it's implied. So we go in the negative direction along the real axis and then in the positive direction along the imaginary axis, and we end up right about here, the important thing being that we're in quadrant 2. So we'll save that information for later, but the next thing we need to do is find values of r and theta that relate to these complex numbers. So at this point, what you want to do is identify the real part and the imaginary part of your complex number. So this is going to be the real part, and this here, negative 2, is going to be the imaginary part of my complex number. What you want to do is relate that to this formula here, or this expression, alpha plus beta I. So plus beta I, where alpha is the real part and beta is the imaginary part. So when we compare the values in our complex number z to alpha plus beta I, what we see is that we get alpha is going to be equal to 2 square root 3, and that beta is going to be equal to negative 2. In other words, we want to identify the values of alpha and beta. Over here for w, what we see is that we have this negative 1 value for alpha, and that we have a positive 1 value for beta. So then we can say alpha is equal to negative 1, beta is equal to positive 1. So again, the first thing we want to do, identify values for alpha and beta. Once we have those values, we can plug them into these two formulas here for r and theta, because we're going to need values for r and theta. So first we'll plug into the formula for r, and r is just going to be the distance of this point from the origin. So this value r that we're finding is basically going to be the value of this distance right here. So I call this r. So that's the value we're finding when we find r. So r is going to be equal to the square root of alpha squared, so 2 root 3. We're going to square that, plus beta squared, so negative 2 squared. We square that. And now we just want to simplify for r. So 2 squared gives us 4, so 4. Root 3 squared gives us 3, so we're going to get 4 times 3, plus negative 2 quantity squared is going to give us a positive 4. So we're going to end up with square root of 12 plus 4, or 16, which is going to be equal to 4. So r is equal to 4. If we come over here and do the same thing for w, we're going to get r is equal to the square root of alpha squared, or negative 1 squared, plus beta squared, or 1 squared. When we simplify here, we're going to get the square root of 1 plus 1, or the square root of 2, which we can't simplify any further. So we get square root of 2. We've got both of our values for r. Now we need to find both values for theta, and we start with this formula. Tangent of theta is equal to beta over alpha. So we're going to say tangent of theta is equal to beta, in this case negative 2, divided by alpha, 2 square root 3. When I simplify here, I'm going to get my 2's to cancel, leaving me with just negative 1 over square root 3. We'll come back to that in a second to solve for the value of theta, but before we do, we'll come and get tangent of theta over here for the other complex number. So we're going to get tangent of theta is equal to beta 1 over alpha negative 1, which is going to be equal to negative 1. So now we have tangent theta equals negative 1 over root 3, and tangent theta is equal to negative 1. This is where our Argand plane comes back into play. Remember that for this first complex number, z equals 2 root 3 minus 2I, we plotted that complex number in the Argand plane here in the fourth quadrant. This is where we want to go to our unit circle. We're going to be looking in the fourth quadrant on the unit circle, and what we're looking for is a value of theta such that tangent of theta is negative 1 divided by root 3. Now remember that tangent is the same thing as sine over cosine, so really what we have here is sine of theta over cosine of theta is equal to negative 1 over root 3. Now remember that when we look at the unit circle, we're looking for an angle theta. Sine of that angle is going to be the y value of the coordinate point there. Cosine of theta is going to be the x value of the coordinate point at that angle theta. So in other words, what we're saying is we're looking for the coordinate point on the unit circle in the fourth quadrant such that the y value in the coordinate point divided by the x value in the coordinate point is equal to negative 1 over square root 3. So if we jump over here to our unit circle, the first thing we want to remember is that, again, we're looking in the fourth quadrant over here, because when we plotted our complex number in the Argand plane, it told us that we were going to be looking in the fourth quadrant. Then we're looking for the coordinate point in this quadrant. There are only 3 options, but we're looking for the coordinate point in this quadrant such that when we take the y value in the coordinate point and we divide it by the x value in the coordinate point, we're going to get negative 1 divided by square root 3. Well, the only coordinate point of these 3 that gives us that is the value theta equals 11 pi over 6, because when we take the coordinate point for 11 pi over 6 and we take the y value in that point, which is negative 1/2, and we divide it by the x value in that point, which is root 3 over 2, that's going to be equal to negative 1/2 multiplied by 2 over root 3. We're going to get the 2's to cancel, and that's going to leave us with negative 1 over square root 3, which is the value here that we needed. So what we find then is that theta is equal to 11 pi over 6. What about our other complex number, w? So we have w equals negative 1 plus I. We know that tangent of theta is going to be equal to negative 1. And remember, when we're looking at the unit circle, we need to be looking in the second quadrant over here. So if we come back to our unit circle then, remember that we're looking in the second quadrant up here, and we're looking for the angle theta, where when we take the y value from the coordinate point and we divide it by the x value from the coordinate point, we're going to get negative 1. Well, we've only got 3 options, and the only option that's going to give us that is the coordinate point at 3 pi over 4, because when we take the y value, root 2 over 2, and we divide it by the x value, negative root 2 over 2, we're going to get negative 1. So if I come back here to my value for tangent theta, what we're going to get is theta is equal to 3 pi over 4. Now with my values for r and theta, I can go ahead and write each complex number in polar form, and I'm going to use this formula here for z. So z is equal to r times cosine of theta plus I sine theta. That's the formula we use to write a complex number in polar form. Z stands for a complex number. That's the variable we use most often to represent it. When I write this complex number in polar form, I'm going to want to say w is equal to, because the complex number was given to us as w. So in this case here, for this first example, I'm going to say z is equal to r, which we know to be 4, times cosine of theta, so times cosine of 11 pi over 6 plus I sine theta plus I sine of 11 pi over 6. That's going to be this complex number in polar form. This second complex number in polar form will be w is equal to r, or square root 2, times cosine of theta, so cosine of 3 pi over 4, plus I sine theta plus I sine of 3 pi over 4. So now we have both complex numbers in polar form. We just need to find the product. And the formula we use to find the product is this formula here. But it's really pretty simple to remember even without the formula, because all we're doing is we take the left-hand sides, we're multiplying z by w. So on the left-hand side of the product, we're going to get z times w. The product of z and w, it's going to be zw, that's the left-hand side. On the right-hand side, we're going to multiply the values of r together. And this formula is always going to work, so all you have to remember is multiply the values of r together, in this case 4 and root 2, so that's going to be 4 times root 2. Then we multiply that by cosine of theta 1 plus theta 2. So we're going to multiply by cosine of theta 1, or 11 pi over 6, plus theta 2, 3 pi over 4, plus 3 pi over 4. Then we add to that I sine of theta 1 plus theta 2. So again, 11 pi over 6 plus 3 pi over 4 for sine. And that's it. So you're just multiplying the complex numbers together, z and w, so you get zw. You multiply the values for r together and leave that out front. And then you add the theta values together. So you add the angles inside of this cosine function, you add the angles inside of the sine function, and now we just need to simplify. So in order to simplify, we'll have to combine these theta angles, and the way that we'll do that is by getting a common denominator. So the least common multiple of 6 and 4 is going to be 12. So to get 6 to 12, we have to multiply it by 2. So we're going to multiply top and bottom by 2. This is going to become 12. This is going to become 22. To get 4 to 12, we have to multiply it by 3. So we're going to call this 12. We're going to multiply the numerator also by 3 and get 9 pi. And of course, that's going to be the same thing over here. This will be 22 and 12. This will be 12, and this will be 9. So then when we do the addition here, what we're going to get is 4 root 2 times, here we have cosine of 22 plus 9 is going to be 31. So we're going to get 31 pi over 12 plus I sine of 31 pi over 12. Now we don't really want to leave our answer like that because 31 pi over 12 is greater than 2 pi. The way that you know that is because, of course, 31 is greater than 2 times 12, right? If we think about this number 12 here and we wanted to get 2 pi out of this fraction, 24 pi over 12 would simplify to 2 pi because 24 divided by 12 is 2. So 24 pi over 12 is a full 2 pi. So 31 pi over 12 is greater than a full 2 pi, but we want our angles to be in the range 0 to 2 pi, so it fits on a normal unit circle or in one rotation around the unit circle. So what we want to do then is subtract a 24 pi over 12, since that's a full rotation, from 31 pi over 12. So we're going to say 31 pi over 12 minus 24 pi over 12, and that's going to be equal to 7 pi over 12. So 7 pi over 12 and 31 pi over 12 are exactly the same angle, just with 360 degrees less of rotation, but it ends up being the same angle between the real axis and this value here for theta. So then we want to go ahead and rewrite the product of our complex numbers as zw is equal to 4 root 2 times cosine of 7 pi over 12 plus I sine of 7 pi over 12. And that'll be our final answer for the product of these complex numbers.